Hi everyone, I'm Sydney. For those of you who don't know me, I'm a second-year grad student and I work with Compass. And I'm here to introduce Professor Robert Lin, who's going to be giving our Compass lecture today. A little about Professor Lin. He got his bachelor's degree at Caltech in 1962 and his PhD right here at Berkeley in 1967. And since then he's worked at the Space Science Lab up the hill. And he's a professor of physics and astronomy here, and in 1998 he became the director of the SSL. And in 2006 he was elected to the National Academy of Sciences, which is very impressive. And they recognized his experimental work studying electrons and ions that are accelerated by the sun, and detecting the accompanying X-ray and gamma-ray emissions. And he's led many successful satellite, rocket, and balloon missions. And most recently, I've enjoyed reading about the MAVEN mission, NASA's new MAVEN mission to Mars, which is planned to launch in 2013. And Professor Lin is leading a group at Berkeley that's building the particles and fields package for the mission. So I encourage you guys to look that up. It looks to be a very interesting program. And today, Professor Lin will be telling us about particle acceleration in solar flares.
Thank you.
Or not now? Okay, great. I'd like to tell you a little bit about some stuff that we've been doing for the last, well, quite a long time. And the interesting part to a physicist is the following. We basically live on the Earth, and this is a very unusual place in the universe. Most of the universe, 99% of it, is filled with a very tenuous gas, which is partially ionized. So basically it's what we physicists call a plasma. This gas is so tenuous that particles don't make collisions very often. So for example, right around where we are in the solar system, a particle will go the distance from the sun to the Earth before it makes a collision. So the well, in the Earth, everything pretty much depends on collisions. You know, even in this room, the density is enormous compared to out there. Out there, you might have one particle every cubic centimeter or cubic meter even, and so they don't make collisions. Yet everything out there happens in this medium, and the way that it happens is quite different from what happens in a relatively dense neutral medium like we have here in Europe. Of course, the fact that we're around means that this kind of medium is conducive to generating life. But if you want to know what goes on in 99% of the universe, you have to look at these very tenuous collisionless plasmas. They might not be fully ionized. And that applies not only to stuff in space, but also to stuff in the atmospheres of stars like our sun. And one of the things that happens, which is quite surprising, at least to me when I first found out about it, is that in these kinds of collisionless plasmas, you can get, it turns out to be very efficient to accelerate particles. Now you guys probably know, if you go down to SLAC or somewhere where they're accelerating particles, they use a huge amount of energy and they get a little bit of it out in particles. But in these tenuous plasmas, often you can convert tens of percent to 50% or more of the energy that's released in these kinds of explosions in the form of high energy particles. How that happens in these plasmas isn't really known. So what I'm going to talk about today is how that happens at the sun. And the reason the sun, of course, is nice is it's very close, and we can make very good measurements. So if you look up at the sun, you'll see this bright disk, and you'll see some sunspots. In fact, this is a good time to go look at sunspots. There's a number of them. But if you go through, so when you first see the quiet sun, it looks like this. It's got a few sunspots. This is at a temperature of about 6,000 degrees, and so it's mostly neutral. Sorry. But if you now look in the extreme ultraviolet, or at say 304 instruments, then you don't see the surface of the sun. You see stuff stuff above it. And this stuff above it is at higher temperature. And in fact, the corona of the sun, the atmosphere, is up at around 1 million degrees. And one of the puzzles is we still don't understand how that works. You've got an energy source at the center of the sun, so it's very hot there. And of course, the heat comes out through various means, radiation and convection, and eventually gets to the surface here, where it's 6,000 degrees. But then above it, it suddenly goes up to 1 million degrees. And how the corona gets that hot isn't really very well known. But if you look at this stuff, you see these sunspots. Now if you look up higher, where it's hotter, so you look at a different wavelength, you notice that where the sunspots are the brightest regions here. And when you look even higher, at even higher temperature, you begin to see not only these sunspots, but you see these little arcs that go across from one end to the other. A sunspot's basically a magnet. It's a very high magnetic field region. And of course, with any magnet, it's got to go from one polarity to the other, right? We know from Maxwell's equations that all those field lines have to be closed. So, and remember now, this medium is ionized, so we have electrons and ions. And a charged particle, of course, feels a force from the magnetic field. In fact, what charged particles would do in a magnetic field, if they're not making collisions, is they'll go around in a helix around the magnetic field. So basically, they're tied to the magnetic field. And so when we see these things, when we see these loops, well, we can use these too. You can see they're loop-like structures here. And what's really happening is that plasma, these charged particles, are tied to the field, so they outline the field. And of course, they're radiating, so that's why we see them. Now, the sun is rotating it goes around about once every 27 days relative to the Earth. And you see now that these things are quite dynamic. Sometimes they brighten. And these are what we call solar flares. And they clearly are associated with the magnetic field in these sunspots. And they release a huge amount of energy in one of these flares. And we could ask, where did that energy come from? Being a physicist, the first thing you think of is you're releasing a lot of energy. It's got to come from somewhere. Well, if you just add up all the heat energy in the gas at that 1 million degree temperature, you find it's orders of magnitude too little energy. The energy's got to come from the magnetic field. So somehow in this kind of plasma, you're able to convert the energy in the magnetic field into an explosion, releasing a lot of energy, and a large fraction of energy comes out in high energy particles. That's the puzzle that I'd like to talk about today, and it's a puzzle that we still don't know the answer to. Okay, here's a flare. This is one of the biggest flares of the last solar cycle. You probably know that the sun varies on about an 11-year time scale. It goes through periods where it's very quiet with no sunspots, and then it goes through periods where it's got lots of sunspots. We're approaching a solar maximum now. There are a lot of flares going on now. So let's take a look at this flare. The kind of dots that okay, so you see what's happening here. This is a picture in kind of a few million degree plasma. And those dots, those regular dots, those are because this telescope, this X-ray telescope, has some bars to hold things inside the telescope. And when the X-rays are so bright, they actually diffract off the bars and produce that pattern. But if you ignore that pattern, what you will see is that there seems to be a lot of loops that get bigger and bigger. You see them? And they're wiggling around. Now remember, we said in the magnetic field, particles will tend to be tied to the field lines. So what we're seeing are a whole bunch of loops going across this linear structure. And this linear structure is getting bigger with time, right? So if you see and the loops wiggle and do all kinds of crazy things. If you think of that as the magnetic field, then clearly what's releasing the energy in this flare has something to do with these loops getting bigger and bigger, right? Okay, so here's a flare that we see on the limb of the sun. So we're seeing it from sideways, and now you can really see the loops, right? And they're getting bigger and so forth. And people have made measurements similar to this for a while, and what they think might be happening is the following. You've got a magnetic configuration like this, where you have a north and a south. You could think of a bar magnet down here would produce these. But up above, the field doesn't look like that. As we get higher up in the atmosphere, because these guys move around a lot, and up here, all the particles are kind of tied to the field line, but they're also blowing out in what we call a solar wind. We'll get to that later. But basically, the magnetic configuration kind of looks like this. There's some closed loops, like the ones we saw in the picture, and there's some field lines that are open like that. We think what happens is in a region up here, somehow the field is no longer tied to the plasma, and what we call reconnection happens. So these two field lines come together and they connect over here, and you end up with a loop down here and a loop up there. And well, that's kind of interesting. It appears that in this region, you're releasing a lot of energy. Now, why do you have more energy? If you just had a magnet down here, we all know in a magnet, the field strength falls off as roughly 1 over r cubed. It's called a dipole field, right? And so when you calculate, and you know you can calculate the energy in a magnetic field because it's b squared over 2 mu naught, right? That's the energy density. You integrate over everything. But if you calculate the dipole field compared to something like this, you'll find out this has a lot more energy. Why is that? Because if you had a dipole field, it'd be falling off as 1 over r cubed, but these guys clearly aren't falling off as 1 over r cubed. There's a lot more. And it's this energy that gets tapped to produce explosions. And it gets tapped in some weird way. Something very odd happens right here. And I'm going to show you that that's the case. Okay, so, all right. So, of course, people have very fancy, complicated versions of this. But this is basically what we think is happening. We don't know what's happening right here. And in fact, that's a puzzle even now. And if you're an experimental physicist, the first thing you think of is how am I going to be able to look at that region and see what's happening in there? What are the physical parameters? What's the magnetic field doing? What's the density doing? And is the stuff moving around? And so forth. So the other thing that we did a long time ago is we looked at the sun at high energy, So when you have a plasma in the corona at 1,000,000 degrees, then it tends to radiate in wavelengths that are comparable to that 1,000,000 degrees. So 1,000,000 degrees turns out to be about 100 electron volts, and that will give you radiation in the ultraviolet, extreme ultraviolet, and X-rays. Remember the first maps I showed, the first movies I showed you, as you got to higher temperatures, you were looking at a shorter and shorter wavelength. So here we're looking at much higher energies. So these guys are kilovolts, and so their typical temperatures are tens of millions of degrees. And in a flare, you probably get the hottest plasma in the solar system, up to as much as 50 million degrees. Down here, you're seeing even higher energies, and you notice it's very bursty. And these, now, we think are produced by high-energy electrons that hit the atmosphere. And when they hit the atmosphere, some of them get very close to a nucleus, and they get slowed down very quickly. And when they do that, you produce X-rays. So your X-ray machine at your dental office, basically it's got an electron accelerator, and they let the electrons hit the target, it's usually some metal, and they produce X-rays through what we call braking radiation, or bremsstrahlung. So we're seeing, we think, bremsstrahlung from energetic electrons up to hundreds of kilovolts, even up to millions of kilovolts. So these are enormously, millions of EV. And also, we're seeing stuff
at very specific energies, 2.223 MeV, a line. This is a gamma ray line. And these gamma ray lines, some of you may know, happen when you take an ion, a proton or a heavy ion, and you hit a nucleus. And when you hit that nucleus, you excite the nucleus, right? And when it gets excited, it then decays back to the ground state by emitting a gamma ray of a very specific energy. So what this is telling us then is there are high energy electrons being accelerated and high energy ions being accelerated. So the question is, how much energy is going into that? So if we're looking at hard X-rays and gamma rays, what's happening is a flare is happening somewhere up in the corona, and it accelerates electrons. They come down into the denser regions, lower down to the atmosphere. This is where the surface of the sun is, where you see the white light emission. And the electrons at tens of kilovolts get down to about this kind of density, and they're producing X-rays by bremsstrahlung. The ions at MeV energies, at tens of MeV, even hundreds of MeV, come down, and every once in a while, one of them hits a nucleus and excites it, and then the nucleus emits gamma rays at a specific energy. And sometimes it also produces neutrons. It breaks up the nucleus. Neutrons come out, and they get captured down here by hydrogen. It's a long, complicated story, but if they get captured by hydrogen, it forms deuterium in an excited state, and it emits a gamma ray at 2.223 MeV, very exact energy. You also produce some positrons, antimatter, and they grab an electron and they produce 511. As you know, the rest mass of the electron is 511 kilovolts. They produce two gamma rays at 511. Yes, the matter, antimatter annihilates. So if we look at a solar flare, we see this kind of a spectrum. At the lowest energies, from a kilovolt up, you see what we call a thermal spectrum. It's as if you have a Maxwellian distribution of electrons, and those electrons are at a temperature of 20 to 40 million degrees, really high energy, high temperature, and they hit the nucleus of stuff there and produce this spectrum, and this spectrum is what you get if you have a Maxwellian distribution. Notice it's kind of curved up here. Then up here we see the higher energy X-rays from about 10 kilovolts to MeV, and those are due to high energy electrons that hit something, produce bremsstrahlung X-rays, but they're not thermal. They go up very high. And then finally out here, you have all the nuclear interactions that produce the gamma rays. Now, what's great about this is we know, for example, in designing an X-ray machine for the dentist, we know how many electrons we need to have hit this target to produce a certain amount of X-rays. So if we know how many X-rays are coming from the sun, we can figure out how many electrons, what energy, and so forth that they need. If you add up all the electrons that are accelerated in a flare, and you compare, you take its total energy, again, like a physicist, you want to look at energy, and you compare it with all the energy that's coming out in the flare, you find that 50% of the total energy released in this huge explosion is coming out in the form of accelerated electrons. We haven't even talked about the ions. If you take the ions, which produce the gamma rays, do the same thing. It's a collision, right? So if we know how many gamma rays there are, we can calculate how many ions there should be. And if we add up that energy, it's also comparable to that. So that to first order, these solar flares, these huge explosions, are huge accelerator. They are putting most of their energy in accelerating particles. Now on the ground, that's incredibly difficult. How it happens in this kind of environment is of course what we're interested in. So let's just summarize this. How much energy are we talking about here? A big flare is equivalent to a few billion 1 megaton bombs going off in 100 to 1,000 seconds. So these are by far the most energetic explosions in the solar system, bigger than anything else you can think of. And the scale of it is so huge, I mean, it's hard to imagine. And at near solar maximum, like near now, these happen about on average once a month. They tend to cluster, but they're on average about once a month. So And as I mentioned, a very large fraction of the energy is coming out in high energy particles. So about 10 years ago, we said, okay, if we want to know what's happening in flares, since most of the energy is coming out in high energy particles, we ought to look at the radiation that the high energy particles are making. Of course, we'd like to go into the flare itself and make measurements, but that turns out to be really difficult. But we can look at stuff, and it's close enough so we can look at details. So we designed a spacecraft that had an X-ray and gamma ray imager on it. And this is not easy because you think of making images with a telescope, you usually think of a lens or a mirror, right? And so the photons reflect off the mirror or they get focused by the lens, and then you make an image. Unfortunately, these energies are so high that it's basically impossible 10 years ago to actually make a lens that would make an image. So how do you make an image if you don't have a lens or a mirror? Okay, we did it by shadowing, making shadows. Okay, and let me explain how you do that. What we do is we got two sets of grids. They're parallel to each other, so linear grids with slits inside and slats, identical sets of grids. Okay, so now you can see these grids are thick enough so that even a high energy photon won't get through. So, and so, for example, for gamma rays, these things are 3 centimeters thick of tungsten. Imagine making these, and I'll show you some of those. So what you can see here is that a photon can get through here, but if I move it a little bit, it can't get through here. So if you radiate photons at this from this direction, you'll see a pattern of stripes, right? The ones that get through give you a stripe. The ones that don't get through, you don't see it. And then we're going to move this whole thing across the source. So say we have one photon. We see it in some location. We can look back through it and we say, okay, it's going to come from these red stripes. It can't come from these guys because it's blocked. So then we move it, say turn it a little bit, and we see some more photons, and then we can see that by using more photons, if they're all coming from the same source, now the photons have to be in these slots here, and by using, say, 20 of photons, we get to this, and by using 50, we get to this, by using 100, we get to this. You notice by the time we get to 100, we can tell where it came from. And so if I have 400, I get this. So we can image by making shadows. So what did we do? We said, okay, we're going to have 2 sets of grids. Some of them, the spacing is very broad, and they make, and some of them, the spacing is very fine. So the fine ones we made could go down to about 2 arc seconds. 2 arc seconds is really fine. It's looking at a dime 2 kilometers away. That's the resolution of 2 arc seconds. Okay, we can get that with this technique. So we have some at 2 arc seconds, some at 3.9, and so forth, all the way up to 3 arc minutes. Okay. The whole sun is 30 arc minutes, and a flare is 3 arc minutes, and so that allows us to see a whole flare. Okay, and so what you're really doing in this, and we rotate this whole thing. So what you're really doing is you're getting the Fourier component of the image at each of these resolutions. So with this thing rotating around, of course, you get different Fourier components at every angle. So if you let this rotate, in half a rotation, you will get a large number of Fourier components. In fact, a typical thing, typical source gets hundreds, maybe 1,000 Fourier components. Then we add up the Fourier components and reconstruct the image. Okay. And remember, the reason we're going to all this trouble is it's really hard. We don't have mirrors, we don't have lenses. We do it. Okay. So the other advantage of this system is that we put one detector behind each grid, and that detector doesn't have to have any spatial resolution at all. If you made a real image, you'd have to have a detector that could see all the different points. But in this case, we don't need it. All we have to do is look at the modulation in time of this. And so we can optimize these to get the best energy resolution. Because, of course, we want to measure the energy of these very accurately, especially if we're looking at a line like this. So we use germanium detectors. These are 8.5 centimeters by 7 centimeter diameter. So they're a big hunk of germanium. And these only work well if you cool them to liquid nitrogen temperature. So we put them in a cryostat like this, and we split it into a front and rear. And that's because the number of low energy photons is hugely more than the number of high energy ones. We want to see both. So the front segment stops the low energy ones, and the rear segment takes care of the high energy ones. Perfect detector. We can't make a detector count to infinity, right? Okay, so then, worse than that, for the biggest flares, we got to put absorbers in front to cut down the low energy stuff so we don't get into saturation of our detectors. And these come in automatically when the counting rate goes up. And then finally, to cool this thing to liquid nitrogen temperature, we use a mechanical Stirling cycle cooler. I don't know if you guys know about Stirling cycles, but they're very efficient coolers. And so that keeps the detectors very cold at around liquid nitrogen temperature. And of course, here's the full spacecraft. So here is the grids at the top and the bottom. Let's see, let me see, did I gotta, that may be later. Here. So here's our telescope. Set of grids at the top, set of grids at the bottom. That's here and here. And that's our telescope. And then below it, we put this, right? The detectors. And then we put it into a spacecraft. These are solar panels. And you see these two guys lifting it. Of course, this thing weighs 280 kilograms. They're not lifting it. There's a hook up above that's holding. So, of course, the big problem with space is you can't fix the thing once it gets up there. So you have to be absolutely sure it's going to work, right? And so the first thing you do is you vibrate this, because you know in the rocket launch you get a lot of vibration. You want to make sure your spacecraft will survive that. So we took it to JPL to vibrate it, and this is what happened. It broke the spacecraft. This is the center of the spacecraft. It cracked it. It turns out they had a malfunction with their vibration table. We asked for it to give us 2 G's worth, and the vibration table gave us over 25 G's. And we were lucky at that point because the bolts holding the spacecraft down to the table sheared. Otherwise, it would have gotten even more. But it basically broke the spacecraft, broke the solar panels, broke our cooler, we went home and thought, oh, Jesus. And then we realized, after looking at all the damage, that we could fix it. It would take us 6 months. It would take us a fair amount of money. I went back to NASA and said, I walked through the door and they said, well, I'm sorry, because that's the end of your mission. And then they were very happy to hear that we could fix it for, from their point of view, a relatively small amount of money. We went ahead and fixed it, and then we got ready to launch again. We were going to launch on July 4th of 2000 because we figured no one would forget the launch date, right? July 4th, 2000. After this got broken, it took us 4 months to fix it. We were ready for launch in November, but the rocket was having problems. Finally, in June of 2001, they said, okay, the rocket's okay. We'll ship you down to Cape Canaveral for your launch. So we got down there. The week before our launch, they were launching an aerospace plane with the same kind of rocket. And that plane went up, the rocket took it up, and suddenly it took a sudden turn like this, and they had to destroy the rocket and the plane because something wrong happened. So then they said, okay, we're going to figure out what happened before we launch you. And I waited and waited and waited. And at the same time, solar activity is starting to come down, and I'm thinking, geez, we're not going to get up there in time to catch these big flares. And finally, though, in February of 2002, we launched. Here's the the new spacecraft rebuilt, sitting on the end of a rocket. This is the fairing that goes around it. This rocket is actually carried right down here underneath an airplane. And the airplane goes up, and this saves fuel, right? Because you can use the airplane to get above, get to some altitude, saves you a lot of potential energy. And then when it gets up there, the airplane drops the rocket. And then the airplane gets out of the way because the rocket is 60,000 pounds of high explosive. If it blows up, they didn't want to take the airplane with it. And it got launched. Okay. So what can we do with an instrument like this? It's got very good spectral resolution. It means you can take a picture in a small region of energy, 10 to 12 kilovolts, up to hundreds of kilovolts. And we can take a picture at every one of those energies. And so you see all of these things. You can see that there's something seen at low energies. This is actually where the thermal part, the 20 or 40 million degree plasmas. But then when you get to higher energies, you see something quite different. And this turns out to be the high energy electrons hitting. And you can see that by the time you get to here, the thermal part is disappearing. It doesn't really go much above 40 kilovolts, and so forth. But of course, a flare happens very quickly. In 1,000 seconds, it's over. And so what you really want to do is make movies, right? Okay, so we make movies. So here's a movie. Now, I want to explain it to you. We're looking at the spectrum and the spatial stuff at the same time. So here I put the spectrum, and here I put, here's the limb of the sun. This flare happened over here. And I'm going to show you two energy bands, the 12 to 20, which is mostly hot plasma, and then the high energy stuff, which is the electrons. And we're going to show you a movie. And this is the variation in time of the fluxes. So let's go show you the movie. And watch carefully now. Remember I told you the spectrum is curved if it's thermal. And you can see here, this isn't curved. This is a power law plus another power law with a. So early on in the flare, the particles being accelerated even before we see the thermal. Okay, so let's see what we have. Okay, I'm going to replay this several times. So you see the thermal part starting, and then you see these high energy things. These are 100 to 150 kilovolts. And notice these guys, there seem to be several spots that are moving away from each other. Remember, we were talking about the fact that in the flare we see these loops that get bigger and bigger in time. Okay. And also notice that now we get the thermal part. See this nice curve? Okay. So you're producing, early on you're accelerating particles, later on you're producing a hot gas. It turns out to be about 40 million degrees. And these guys are moving apart. So now, remember we were saying, we think we've got this situation where this magnetic field coming together, somehow we're reconnecting, so these two field lines become a loop like this, and then stuff goes up there. And you can see now that if we're accelerating the electrons there, that the electrons will come down here and hit the surface and produce the X-rays. So they'll produce two spots. But the next batch will be two spots that are further apart. Okay? You see, this was the old two spots. The next set of field lines comes in, and it's so that movement outward is actually a measure of how fast these field lines are reconnecting. And you remember I said the field that's up like this is much bigger than a dipole field. And so when you convert from a field line that looks like this to one like this, you release energy from the magnetic field. How it does that is the trick. We still don't understand that. But we can clearly say that they are doing that because we can take a look at two of these foot points that we talked about that were moving apart. We look at their time variation. One is in red, one is in blue. And you can see they track each other really well. And that's exactly what you'd expect if you accelerate electrons up here. The electrons are traveling a good fraction of the speed of light. So they zip down here and they hit these two things essentially simultaneously. Yeah. And so basically, we know that's happening. We can also look at the magnetic field. over here, white is magnetic field of one polarity, and black is the opposite polarity. So you expect loops to go from black to white to be a field. And now I've shown you where the foot points are, these that are moving. And you can see that they're basically making a whole bunch of loops here with time. Okay? And so we have very good evidence, I think, that this process is happening. But what is this process? Some kind of physics is going on, which we don't know. Okay. So, of course, if we go back to this figure, we'd like to look at this part, right? That's where all the action's happening. But that part is high in the corona. The density is low. And, of course, X-rays get produced by hitting things. So the higher the density, the brighter the X-rays. Okay? And so that part's really hard to see. And especially if we're looking at these parts where the density's high, these get very bright, and we're trying to see a weak signal up here. And that's the one thing that this kind of imaging can't do, because when you remember, we're just looking at strips, and strips from a bright source is going to mask the strips from a weak source. So we can only see things with a dynamic range of about a factor of 10 to 30. That is, the brightest source can only be about a factor of 10 to 30 brighter than the weakest source that we can see. So if it's a weak source, we can't see it. So how do we get around that? Well, sometimes the flare is over the limb of the sun. So we caught one flare like this. Here's the Earth over here. It can't, of course, the X-rays can't get through the sun, and we just see the top. There was another spacecraft looking from here that could see the flare here, and we knew there was a flare going on. We were seeing just the top. That's exactly the region we want to look at, because that's the one that everything's happening. Here's what we saw. Here's the limb of the sun. Here's the X-rays from the hot plasma. And here's the X-rays from the high-energy electrons. The interesting part is this thing is not here, but actually above it. That's where we think things are happening. We also saw this with a radio telescope. And radio emission comes from these electrons gyrating in the magnetic field. And so the intensity of the radio emission depends on the field strength. So by using these two measurements, we could look at the region that we were interested in and figure out what the magnetic field is, and also how many electrons and stuff were there. And the first thing we noticed was that we didn't get any thermal emission. I've already said that. This is thermal emission from before. We just see high-energy electrons. Okay. And the whole source is filled with high-energy electrons. These electrons extend up to a megavolt, because that's what it takes to make the radio emission. And if we now calculate the parameters that we get, since we image it, we know how big it is. We get the magnetic field from the radio emission, okay? And we know the density beforehand, and the density afterwards is about the same. But now, but beforehand, it was just ambient thermal electrons, and suddenly they've all converted into high-energy electrons. So this thing suddenly accelerated all the electrons in the thing up to tens to hundreds of kilovolts. And if we calculate how much energy is in these electrons and compare it with the energy in the magnetic field, it turns out to be about equal. That's what is meant by beta equals 1. Beta is the ratio of the particle energy to the magnetic energy. So what might have happened? The magnetic field there somehow got converted into energy particles, and it continued to do that until half of the energy in the magnetic field is converted to particles. People have ideas about how you might do that. I'm not going to explain this, but in the reconnection process, you can have many, many reconnections, so you make many loops like this. The loops, of course, you know there's magnetic tension, so they want to become round. They don't want to stay elongated. And when they do that, if you have an electron that's running around here fast, each time it gets to the end, it gets a push because the thing's going in. So it's getting pushed on both ends, and it continues to gain energy. Now, who knows whether this is right? Our measurements aren't good enough to tell us. That's what we would like to do next time. Okay, what about ions? Ions, gamma rays are much fewer gamma rays than X-rays. You remember the spectrum falls really fast. So that for every X-ray that we see, there might be only 1/1,000,000th the number of gamma rays. So we don't get many gamma rays. But in the biggest flare that we saw, we got enough gamma rays, and our technique, the good thing is we can image anything. It doesn't have to be energy limited, because all we're doing is shadowing these things. So if we look at the gamma rays, they look like this. The X-rays look like this. The image was made through the same part of the instrument. And this is this flare. You see all these loops. Now, you see these 2 foot points for the X-rays. We said that's because we're reconnecting up here and forming a new loop. We had to integrate over the entire flare to get these because the gamma rays were so low. But you notice they also have 2 foot points. That suggests that the ions, which produce gamma rays, are accelerated in the same process. But we also know from this that their offset, this is a real offset. We don't understand why. If electric fields are involved somehow in the acceleration, they could, of course, separate the 2 species. So we suspect it has something to do with that. All right. So now, we've been talking about flares, but things are happening elsewhere, too. Here's the sun, and this stuff coming out is called the solar wind. It's flowing out at 400 kilometers a second. Along comes a flare, which we see. The red stuff is the thermal part, and the blue stuff is the high energy part. And right at the time the flare happens, this enormous amount of material gets ejected from the Earth, from the sun. And at the end, you see all these lines here. What that is high energy particles hitting the detector and making noise. So, and if we go back through this, the flare happens, you have to remember that we said the flare is due to reconnection, makes field lines that close at the bottom. And that, of course, is happening here, down here, right down here. And at the same time, something goes off the other end. And we think that other thing that goes off the other end is this. The amount of material that it throws out is equal to the total mass in the corona of the sun. It's an enormous amount. And it's thrown out at very high speeds, at up to 2,500 kilometers a second. So this is a model people have for it. This is so what they think is that originally there's stuff like this being held back by fields above it, and then you get this reconnection. Down here then you'll get the flare, and then this thing goes out. Of course that's a theory. To experimentalists, you think, well, it's another theory. We'll see whether it's right. When it goes out, and this is stuff going out from the sun, this is the sun here, then you often see the material going out here, and then a thin thing out here. We think this is a shock wave. Now, when you have things that travel faster than the speed of waves, you're going to form a shock in front of it. So a supersonic airplane is traveling faster than the speed of sound, and then a shock wave forms in front. And what happens at the shock wave is the stuff that's coming in faster than the speed of sound gets slowed to below the speed of sound. And then, of course, the density has to go up because you're pouring more material in, right? And so you get a density jump there. That stuff goes out into the solar system. Remember, the sun is rotating, so the magnetic field from the sun gets just like a sprinkler making circles. It becomes spiral-like. But when these huge explosions happen, they completely destroy what's going on. And these huge explosions and the CMEs, the coronal mass ejections they get in, produce all kinds of effects at the Earth, at other planets, and so forth. You probably heard that there's something called space weather. The most extreme kinds of space weather are driven by this kind of stuff. These huge flares with CMEs. And they accelerate particles. So if we look at S, that's a shock, and these red lines are the flare. So here's one of the biggest flares of the last solar cycle. And right after it, you see in the interplanetary medium near 1AU, high-energy particles coming out to hundreds of MeV. And then when the shock goes by, you see a big peak in high-energy particles. So we think the shock is accelerating these particles. Sorry. Okay, so let me just summarize this part, which is you get these fast coronal mass ejections, most of the time at the same time as a flare. They're slower. They take some hours to get out far. But they have about the same amount of energy. You know, another few billion megaton bombs coming out. They throw 10 billion tons of material into the solar system at a speed of several million miles per hour. And it accelerates particles to very high energies. Of course, these particles are quite dangerous. If you're an astronaut out there and one of these things goes off, you will likely die of radiation poisoning. Okay? And in the Apollo program, they had the astronauts saw on the moon, and a few days after they came back, one of these huge flares went off. So they were very lucky to avoid that. And of course, it not only is bad for humans, it degrades electronics, it can kill satellites and stuff like that. So a lot of people are interested in that. Now, of course, from our point of view, this is a physics problem. And this is if we solve it, this is just something else that happens. Well, how can you accelerate particles in this situation? If you've got a shock, you've got material coming in here at high speed, supersonic, and then it slows down to low speed. Supposing I have a particle that goes from here, gets across the shock, bounces back, goes over here, goes this. Each time it goes back and forth, it gains energy because you basically, these two plasmas have a differential velocity, right? And if you make enough of these bounces, you can get, each time you'll gain momentum of this much, where this is the velocity difference here, and v is the velocity of the particle. And people believe that this is how cosmic rays are accelerated by supernova shocks. You know about supernovas. Supernovas are a huge explosion at the end of large, heavy stars, life. And then it produces a huge ejection. And that gives you shock waves, and then that produces cosmic rays, which it turns out have the same energy density as matter or starlight or cosmic background radiation. So it's one of the major forms of energy in this universe. Same process, we think. Of course, we'd love to be able to, if you look at a supernova, you have a hard time figuring out what's going on. But things like these shocks in the solar system, we can actually study them in great detail and figure out the physics. Okay, I wanted to show you this thing, which is the Chandra satellite, looking at one region, a star-forming region in Orion. And look at all these flashes. Every one of those is a flare. So it turns out that the sun, when it was younger, if you look at early solar analogs, they're much more active at that time. They produce flares that are hundreds of thousands of times more energetic. And they're going on all the time. So,
Professor Lin, is that real time? Is that
no, that's 14 days of data.
faster than
Yeah. So these flares typically last for about a day. And so but you can see all these stars are just going bang, bang, bang. Yeah. That's actually very important because the sun presumably did this early on too. And then you have to ask yourself, if it was doing that, what's happening to the planets that are getting zapped by these enormous things, right? Well, they lose their atmosphere, for example. And maybe how Mars lost its atmosphere. Okay, so what are we doing now? Well, we'd like to look at that region where things are happening, which we can just barely see. We'd like to have good measurements of that. And to do that, we're going to try to make, in fact, we are making focusing optics. They weren't possible 10 years ago with the kind of resolution, the angular resolution that we want now. But now we figured out how to do it. And we can get up to about 80 kilovolts. So what we do is we make a shell, two sets of shells, that reflect the X-ray at a very glancing instance. And it has to be a really fine glancing instance. And by those two, you can focus them down to a point, make pictures. And the focusing is really important because, first of all, the detector is very small, and there's a lot of area here. So your background in the detector is small. And second of all, you get very good point response functions. So you can see a much bigger dynamic range, factors of hundreds to thousands. So that means we can see that faint source on top of the bright foot points, okay? And so we can see both parts now. And of course, this is being built for the first time. And there's my graduate student, Lindsay Gleesner. And it's a researcher, Sam Crocker. Can't really make out these guys. This is the rocket it's going to go up in. A rocket only lasts about 5 minutes. We can't catch a big flare in 5 minutes. But little flares happen much more often. We see them maybe every few minutes. And there's a lot of ideas about how to heat the corona. Remember, we said there's some reason the corona is much hotter. One of the possibilities is that very, very tiny nanoflares, flares that are 10 to the minus 9, the size of the flares, which are going off all the time and heating stuff. If they're going off, this thing will see it. Even in 5 minutes, we'd expect to see a dozen or so. And so we're going to go look at that. What about the ions? Okay, the ions are tougher. And one of the problems there is that, as I said, ions don't stop very easily. We have to have thick grids to do the imaging. And if they're thick, we can't space them very close to each other. So instead of spacing them close to each other, we're going to move the grid. This is 8 meters long. And then we put the detectors back here, and they have spatial resolution. This whole thing weighs about 2 tons. And okay, we've flown balloon flights weighing 2 tons before. And but to catch a big flare, you got to be up there for a long time. So you want to have your balloon up there for at least a month, maybe more. Where can you do that? You go to Antarctica during their summer. The wind's set up so it goes around the pole. Great, because now your balloon will go around the pole, right? And here's a ultra long duration flight that they did only 2 winters ago. And wound like this, 50 days. So we want to stick this thing, and of course the other good thing is in the summertime, there's 24-hour sunlight. You can see the sun 24 hours a day, and we can have solar panels to power everything. So this is like a little spacecraft. It runs by itself, goes, looks at the sun, and then we use very fancy kinds of detectors. These are new detectors that have 3-dimensional position resolution in gamma rays. And then we use a fancy kind of grid, which we rotate in front, and then we can make images with this. So Nicole Duncan, who you know, is working on this project. And maybe our first flight should be 2012, fall in the US to check out everything. And then at the end of 2013, we hope to do this. Okay. All right. Of course, if you want to look at flares, what you really want to do is get up in space and sit there for years. Because even 50 days, you're not guaranteed that you'll see something big. So what do we have in mind? We want to put a spacecraft up like this that has FOXY, which is the X-ray imager, and the focal length is so long, you want the optics 10 meters away, and it forms an image down here. And the gamma ray instrument, of course, likes it to be 10 meters away too, so it's over here, the imager and me. And of course, you can't fly it like this. You have to have one that's retractable. Starts out closed up, you know, fold up all the solar panels, put it inside the spacecraft, inside the shell of the rocket, launch it, and then open it up, put the boom out, and so forth. We're not going to be able to do that for this solar maximum. It's already here almost within a year or so. But we hope the next solar maximum, 11 years. Okay, so one last note I want to leave you with is, I was telling some of you that I've had 5 PhD students finish in the last 2 years. I have 3 students working now, but we're looking for more students to work on some of these projects. for a grad student, a rocket or a balloon is just perfect because it takes a few years and you get the data, and with these new kinds of instruments you get really cutting edge data. At the same time you can work on stuff from our RESI satellite to look at the, that's exactly what Nicole is doing. And we're looking for a few more students. We also have a lot of undergraduates working for us, either doing data analysis, helping us with experiments and stuff. So we also tend to have a fair number of undergraduates working. So if you're interested, send me an email. Okay, thank you. Yes.
So hear about the muons. That we get a high energy particle hits the atmosphere, we get a muon down.
Right.
Is this where we're going to get those high energy particles? Because you're saying that they get to a couple MeV. Is this powerful enough to create a muon? A flare will accelerate ions like protons
up to G or tens of GeV, and then the muons are a secondary product.
So we get one of these 10 GeV protons, and that
right.
we get
Right. In fact, even at a few hundred MeV, they start making muons and pions and stuff. Now, there's a satellite up there right now that's doing gamma ray imaging or gamma ray measurements of the sky called Fermi. And of course, when the sun goes off with a flare, it sees them whether it likes to or not. But it's very good because we can tell how high in energy they are. But certainly, we've seen for flares well over a GeV, and for those coronal mass ejections, up to tens to 100 GeV. So they go way up in energy. In fact, the first solar particles were seen on the ground. They saw a ground effect. And to get a ground effect, you have to be well into the GeV range. And of course, what you see is the shower of secondaries, right? Muons and stuff. So the sun is it's the most powerful and most energetic particle accelerator in the solar system. And it's also the most powerful explosions by a long shot. Nothing else compares in the size, in the solar system.
How high do gamma rays get?
Well, people have seen the pion decay gamma rays, which are 70 MeV, peak around 70 MeV. And there's been gamma ray continuum seen even out to a GeV. Okay, and that you need the way they do that is they go to mountaintops. Okay, they have mountaintop detectors, neutron monitors and stuff that can see it. So on a spacecraft, it's hard for us to do that. I mean, a GeV particle it'll go right through anything we try to do. But we get to see all the lower energy stuff, and of course the bulk of the energy in this is low energy stuff, right? I mean, we get a few. What's interesting is how high energy can it get? We don't really know that yet. We know they're into the GeV range. Even the electrons into the hundreds of MeV range. So these are really pretty spectacular. And really the only reason we see them is because they're so efficient at accelerating particles. So you can kind of see why that happens. If you've got a lot of collisions, a particle gains a little energy and it hits something and it loses energy, right? So you've got to have a situation where you don't have too many collisions, then you can accelerate things to very high energies. Yeah. Yes?
Is it well understood where the 11-year cycle comes from?
There are people who think they understand it, and there were predictions about when this solar maximum would come up, and every prediction I know of was wrong. It stayed at minimum for a long time, and we began to think maybe we're not going to get a activity cycle this year. There were times when there were no sunspots. Back in the, I think, 1700s, there's a time called the Maunder minimum when there weren't any sunspots seen. So the solar cycle went away. And those were also the times of the Little Ice Age in Europe. And people kind of wonder, is it connected? Well, with one or two things, how can you tell? Yes?
So can you actually get the energy spectrum of the ions and
yes.
the emissions? So how do you do that?
Well, because certain gamma ray lines different gamma ray lines have different cross sections, right? One gamma ray line might only be excited by a a proton with more than 30 MeV energy. Another one might be 2 MeV energy. So if you look at all the lines, I didn't show you that. We got a lot of others. You can get the spectrum just by saying, okay, these had to be excited by higher energies. So you can get the spectrum, and you can get the number. You can get the total energy. But one problem is we can't see stuff below a few MeV because there are no gamma ray cross sections that are large enough. So, well, if we had really good sensitivity, we'd get down lower. But
so is it not thermal spectrum of ions?
Absolutely. Both the electrons and ions are power law spectra. They're not Maxwellian at all. Yeah, I should have mentioned that. The Maxwellian part, you could see, is that curved spectrum. Yeah, so we know, and those are really interesting too because that's a plasma of 40 or 50 million degrees. I can't think of a hotter plasma in the solar system. That's the hottest. It's really hot. Yeah.
By the way, then is that power law exponent the same for both proton and electrons then?
40 or 50 MeV is 40 or 50 million degrees is still only 4 or 5 kilovolts. We can't even see the protons at that. We only see the electrons through their emission because the protons won't make any gamma rays. Yeah, yeah, they're too low in energy to make gamma rays. Yeah. Yes.
So what happens to the Earth if this big,
CME?
Yeah, coronal mass ejection.
Okay. Okay.
Especially since it's
okay, that's a really good question. What happens is, you got all this high-speed stuff hitting, and of course it's going to compress the Earth's magnetic field because it's got a lot of pressure. And when it compresses the Earth's magnetic field, you have a sudden change in B, and that's going to induce currents on the sun. So the very first flare that was ever seen was seen in 1859 by a guy named Carrington. He saw the actual white light emission in the sunspot. But then soon afterwards, within a day or two, there was this huge jump in the magnetic field of the Earth, which he suspected was due to that, of course, due to that, somehow connected to the flare, but he couldn't prove it. Well, the currents induced by that were so great that some of the people who had telegraphs suddenly got fires in the telegraph office because the currents were so huge. Okay, so they kind of knew that something was going on. And he said it must be from the sun. And other scientists at the time said, you must be crazy. It can't be from the sun. And okay, so, but yeah. So what happens at the Earth now, we know, and we're dependent on satellites sitting in the radiation belts, right? All these geosynchronous satellites. When you compress the magnetosphere, it energizes all those particles in the radiation belts, and satellites die because of it. You also get these currents into the power grid, and they've been responsible for blackouts. So now the commercial sector is very interested in understanding what's going on because it can lead to big effects. Because we're such a technologically advanced society, we depend on all these things, right? So yeah, it is pretty interesting. But as I said, I think it's interesting as a physics problem. How do you convert that energy? We still don't know. We know that it happens. We know where it's happening. We know the effects of it. And to really see what's going on, we need to look right into that region. And that's our next step. Yes?
Would there be an advantage having a satellite, a few solar radii away from the sun?
Sure. Someone asked me this question, are we planning to send a satellite into the sun? Okay. Well, of course, it's very hot. Okay. But if you think about it, here's the Earth orbiting the sun. It's going about 30 kilometers a second. Basically, to get into the sun, you've got to slow it down so it'll drop into the sun. Okay? It takes an enormous amount of propulsion to make it drop into the sun. Once you get it to drop into the sun, if you stay very long close to the sun, you'll burn up, right? So NASA has a mission that they've started called Solar Probe Plus. It will drop a spacecraft into within 10 solar radii of the sun. That's 1/20th of an AU, so 95% of the way in. And it'll be in a highly elliptical orbit. That way, when it gets close, it zips through that and comes back out. So, okay, and that started. And our laboratory has several of the experiments on that spacecraft. By the way, if you guys have never been to the Space Sciences Lab, you ought to come and visit. We have, our biggest problem is we're far away from the campus. We're at the very top of the hill. We have the best view of the bay of anybody. If you look up there, the building at the very top, that's our lab.
LBNL?
We're above LBNL.
Are you associated with them? Or?
No, we're not. We're part of the Berkeley campus. We're an organized research unit at the Berkeley campus. So it's set up so that all the space kinds of things, and it takes very odd kinds of stuff. You know, the fact that you can't fix something means you've got to make things and be absolutely sure they work. So, you know, we don't pay 10 cents for a resistor, we pay $100 because that resistor's been tested. They take 1,000 resistors and test them, and if all 1,000 make it through, then they sell it to us. Of course, it costs us 1,000 times as much. So, and then you test it like crazy because you can't afford for it not to work. It's not like a lab experiment doesn't work, you can go fix it, right? Yeah. So it's very unusual kinds of fabrication and design and so forth. And so you need a special lab for it. And there wasn't enough room on campus to build it, and so we ended up there. But if you guys are interested, you know, send me an email, come up and visit, because it's really quite, I think, obviously I thought it was really an exciting place to work. After I finished as a grad student, I had built an experiment. It wasn't going to get launched after I left, or if I left, and I thought, well, I may as well stick around and see what happened. And ended up sticking around for decades. So, yeah. Okay. Any other questions? No?
Yeah.